In this video, we're going to sort of take a little bit more of a look at the concepts of locality and causality in classical physics. And so these are two interrelated terms because if we think of causality, so we have, some object here and it's going to cause something with this object here, then then locality says that there has to be some intermediating force or something happening between the two, whether this thing actually moves towards it and actually touches it, or if it's giving off some kind of force, electromagnetism or gravity or something like that. So there has to be sort of a touching between these two things in some way, mediated by something, some kind of force. And so then the idea then too is that if we have this object here and this object here, but also this object here, if this object here then gives off in all directions some kind of force, it's going to affect this one before it affects this one. And so that's sort of the idea of locality, that the closer something is in space and time, then the faster it will be able to make some effect on that object. All right, and so Maxwell's equations are sort of the way that we know that electromagnetic waves propagate at the speed of light. And it was actually this insight that sort of led Einstein to the special theory of relativity. In fact, if you see like his original paper, it actually sort of discusses it in terms of electrodynamics, because that was sort of the motivating reason for why Einstein came up with the special theory of relativity. But to see this, so the first thing we can do is take the curl of Faraday's law. And so this here was Faraday's law. And so we take the curl of both sides of that equation, then use this vector identity, which I'm not going to prove here, just know that this is an identity, that the curl of something is equal to the gradient of the divergence minus the Laplacian operator acting on that vector there. And so when we do that, we can sort of trade this part out for this part right here. And so we have the curl of this magnetic field right here, which we're just now putting into this partial derivative with respect to time. But we also know from Gauss's law and Ampere's law that this divergence of the electric field here is equal to this this rho over epsilon naught, where this is the density of charge in a region. And we also have from Ampere's law that the curl here of the magnetic field is equal to this. So where this is the current, and this is the change, sort of the strengthening or weakening, essentially, of the electric field in time, over time. And so when we make these substitutions, we get this, and then when we collect sort of these electric field terms on the left side, and then these source terms here on the right side of the equal sign, we end up with this right here. But when in a charge and current free region of space, these source terms on the right here will just go to zero, and so we end up with this right here. And we could do the same thing for the magnetic field if instead of taking the curl of Faraday's law at the beginning, we did it with Ampere's law, we would get this. And so we see these are both pretty much the same equation, except that we have the electric and magnetic fields in here. And both of these are the form of the wave equation, which looks like this. So we have the space derivatives on the left side here. So the the second order space derivatives and then the second order time derivative on the right side of the equation there, and then this right here, which where v is the speed of the propagation of the wave, which in the above two equations is equivalent to this permeability and permittivity of free space here. And so if we sort of suggestively put c in for that, then we get this for it. So 1 over c squared, which if we do a little algebraic manipulation, we see ends up being this. And so if we actually put those two constants in for the mu sub naught and epsilon sub naught, we get this right here. And so then when we actually calculate that out, we end up with this, which is the speed of light. And so the speed of light just comes right out of these Maxwell's equations. And so what this is actually saying with these two wave equations is essentially that if we have this moving fast enough, then we have this self-propagating electromagnetic wave where from Maxwell's equations we know that this changing electric field will induce a magnetic field, but then that changing magnetic field will then induce an electric field. And so we get this self-propagation when it's actually moving fast enough. So if it's not moving fast enough, what you'll see is that all of the waves will dampen down and eventually go to zero. But if it's moving fast enough, so if the electric field is changing fast enough, it will induce a change in the magnetic field that is fast enough that then induces an equal change in the electric field and so on as it sort of propagates this way. And so we can actually look at kind of how that appears here. And so this is just from Wikimedia Commons. And so we see here we have our electric field in red and our magnetic field in blue. And so we see that the electric field is sort of oscillating up and down, and the magnetic field is oscillating in the transverse direction from that. And this sort of increase and decrease in these fields, which if you look at sort of a single point here, you're just seeing sort of an increase and decrease in these fields, but it creates a sort of directionality to it because of the way that they are sort of inducing changes in those fields in each other. And so that is sort of how an electromagnetic field, that's sort of how light propagates through, even empty space. It can be self-propagating. So like I said, this is the speed of light here. But if we don't ignore these source terms in this red boxed equation up here, then we set these source terms to just some function here. So we can just set it to some function where there will be a different function like this for each of the Cartesian components, so the x, y, z axis. But we also have two wave equations which will in general look like this, where this psi could be either the electric or magnetic field, which means there would be a total of 6 equations. So the 3 Cartesian components times the 2 types of waves, electric and magnetic. So if a charged particle popped into existence at some position that we'll call x prime here, and at some time that we'll call t prime, so a particle which is we can sort of model as a delta function, so our source terms will be this delta function here, then what we get is this right here for our field right here. And so that means that the source at this x prime t prime gives rise to a non-zero field psi, with only where this is equal to 0, or where the time is equal to this time of the that the particle actually pops into existence plus this this sort of change in the distance. So we're looking at a growing distance that's growing at a speed of c right here, so the speed of light, which means only positions x at time t reached by a signal propagating at this speed c. And so the field essentially is propagating at the speed of light in a sort of spherical shell from the source. So our point particle here pops into existence, then at some time t1 it will be at this space here. Then at some time t2 it will be at this space here, sort of propagating outward in all directions. And so this is known as the future light cone of the source. And so if we sort of remove one of the three dimensions and just look at 1 and 2 dimensions here, where this is a dimension of time pointing upward, then that would look like sort of a circle propagating outward from this point here in space and time. So we're looking at this point in space in time, and so that field would then propagate outward that way. But we can also look at the past light cone of some point in space and time right here. And so that is sort of all the points in space and time in the past that could actually exert some influence on that point there. And so, something right here in space and time at this point would not be able to influence this point right here because it's not within that past light cone there. And so the image on the right tells us that this green particle at this point x t in time feels, and this would be via the Lorentz force law, is from states, the other two particles, at some time in the past. And so this point right here is feeling the effects of this particle right here from this point in the past right here. If we're saying that this particle at this point is giving off some sort of field that moves at the speed of light. Right, so we can think of causality a little bit more formally using John Stuart Bell's formulation of causality. So we have some event chi here at the point in space-time xt, where an event is just some description of something at that point. So it's maybe the momentum of a particle or the value of a field or something like that. So we can take a slice of space-time in the past light cone of chi at this point in space-time that we will call sigma here. So it looks kind of like this. So we're taking this slice that I have in gray here and we're calling it sigma. And we can give a complete description of all events, so all the momenta, field values, and so on that slice, and we'll call that C sub sigma. And so C sub sigma is the sort of description, the complete description of all events at that point in the past light cone. So the event chi here is completely determined by that description, which we can represent like this. So the sort of description of this event is completely determined by all of the events occurring in that point in space-time. So we can think of this particle B here, while inside the light cone, is also fully determined by some light cone of that fully intersects this sigma here. So if we look at the past light cone of B here, it's fully intersecting this past light cone while the B is inside the light cone here. So once it got to right here, for instance, then it's now picking up influences from things outside of the light cone of this chi right here. And so this gives a picture of relativistic local causality that is completely deterministic. And so to be more general, we can say that the probability of some event chi, given that the the complete description of a part of its past light cone sigma will be equal to the probability of chi given that complete description and this other event chi here that is not in the light cone. And so we're looking at chi1 here and chi2 right here, where this is our sigma for chi1. So it means that the probability of the event chi1 occurring, given a complete description of events on the space-time slice sigma, is equal to the probability of the event given this complete description in some other event chi that was not completely causally influenced by this sigma. So we see the chi2 past light cone is sort of missing this this sigma right here. So what the equal sign in this means is that the events at chi2 should not change the probability of some event occurring at chi sub 1 right here, because these are not within each other's light cones here. And so we can actually expand on this and just say that the probability of chi1, given this complete description at sigma, and chi2 is equal to the probability of chi1 given this complete description at sigma and not chi2, meaning that the probability of chi1 occurs will not change whether or not chi2 occurs. So for instance, if we have a particle of mass capital M is stationary between these two masses m sub 1 and m sub 2. So we have this m sub 1 and m sub 2. And this is our capital M, and it's sort of equidistant between them. And these, the m sub 1 and m sub 2 are both of equal mass. So this mass m here is stationary between these that are very far away from each other. So whether or not chi2 happens or not happens, then something happens to the M2. So whether this happens or this doesn't happen, so whether this sort of changes path or doesn't change path, this should not make a change in chi1 here. So in other words, it shouldn't cause a sort of gravitational shift in this this mass m right here. So our mass m being right here in our lowercase m2 either changing or not changing direction right here should not change the path of this this uppercase m, at least not instantaneously. And so, you know, we're looking at the sort of past light cone of this sigma here, of this event chi sub 1 right here. And this chi sub 2 either not happening or happening should not actually change that the whatever happens here at chi sub 1, whatever might be happening to our uppercase m right there. But anyway, that is sort of the description, the sort of general description given by John Stuart Bell of causality. And so causality being relativistic and deterministic. And so remember, we're looking at whether this is relativistic and deterministic. So relativistic just meaning that the speed of causality is the speed of light. So, you know, something over here is not influencing that instantaneously when it's not inside that light cone. But also deterministic in that, that something that happens here at chi is completely determined by a description of everything on this time slice here at sigma. And this, where I put this sigma is arbitrary. We could have, you know, put it sort of down here or up here as well. But what matters is that everything in the light cone of chi completely determines chi. And so it's relativistic, it's local, meaning that, you know, whatever happens, you know, right here sort of has to make its way up to chi right here. So, you know, it has to be local. So it has to sort of come to chi in order to determine chi there. And like I said, it's completely deterministic. But anyway, I don't want to ramble too long. I hope you found this video interesting, and I will see you in the next one.